All right, guys, welcome back. Today we're looking at Module 2, Lesson 2. This focus question, how do heaters get warm without a flame? And the one thing I want you to also know is the I can. What can you do? What can you learn? I can chart data and use data to explain a phenomenon. So I can chart data and use data to explain a phenomenon. So how do the flameless heaters work? And yesterday a lot of people said that it has to be similar to hot hands. So we got some hot hands. We'll test that. We have some flameless heaters. We're going to test that. Yeah, so basically the goal today is I want to make sure you understand what temperature is and what temperature is not. Temperature is very loosely, my first graders in first grade, they're told temperature is how hot or cold something is. Sure, very basically, temperature, how hot or how cold something is. But what does temperature really represent? And that's what we try to think about. So if I have a thermometer and I want to talk to you about temperature right now, it's inside my hand, it's about 30 degrees C. What does that mean? And the definition that we use for temperature is the average kinetic energy. So on your paper, if you're following along down here, the definition we're going to use for temperature, the average kinetic energy of the particles being measured. So kinetic energy, remember, there's potential energy. Potential is energy that's stored. A bowling ball at the top of the steps. Potential energy. If you roll it down the steps, as it gets closer to the bottom, less potential, more kinetic. Kinetic energy is the energy that's being transferred. Kinetic. What that means is as particles, as you know, remember solid, liquid, gas, the phases of matter, solid, vibrate in place. The particles vibrate, but they're not free to move around. Liquids, they can move around each other, but they haven't escaped each other's intermolecular forces. So the intermolecular, the forces between the molecules are still holding them together. Yes? Gases, as they get hot enough, they escape each other's intermolecular forces. They can move around wherever they want. Actually, they don't want, but they move around wherever. So temperature, average kinetic energy. As a gas or as a liquid gets hotter, it starts moving faster. Say we're boiling water. The particles in the water, as it heats up, begin moving faster and faster and faster and faster and faster and faster and faster until they escape the intermolecular forces holding them to the group of water. So now it can go off as steam. It's a gas. It's gone. The hotter it is, the more times it's going to come in contact. So think, if I wanted, whoops, forgot that was on. If I wanted to give something energy, if I touch it, I'm giving it a little bit of energy, a little bit of energy. If I wanted to give it a lot of energy, the more I hit it. I'm trying to think of a game, whack-a-mole maybe, Tetris, some game, y'all may not even know Tetris. Oh, I'm dating myself. But some game, the faster you click, the more energy you give it. You touch, energy, less energy. Even just look at me, I'm expending less energy to do this. So the average kinetic energy, how many times those particles are moving and hitting the thermometer is really what we're measuring. The average kinetic energy between the particles. So also on your paper, you'll notice over here, this was kind of our consensus model. As I walked around yesterday and looked at all the models you were drawing, I noticed we had the MRE heater. We had the MRE heater, and just like it looks like, a lot of you drew the 4 parts of the MRE heater. Some of you put food over it. I put the food here with the heat coming off the food, the steam, the gas. And for those that were paying close attention, that gas is hydrogen. Vapors released by the activated heater contain hydrogen, a flammable gas. Do not place near an open flame because it will do what hydrogen does. Let me get that back in there. Let me get that back in there. Okay. So, and then we zoom in before we add the water. So we zoom in, and I hope you're looking at this on your own screen or you have one printed off, because I'm sure you can't see this. So they zoom in and there's particles, and the particles are just sitting still. They're not doing anything, barely moving. They're solid. They're vibrating, but they're barely moving. We added the water and something happened and the particles started moving faster and faster and faster, and we released hydrogen gas. So remember back to signs of a chemical reaction, releasing a gas is one of the best signs, right? Yes. Also, what's another good sign? Color change and rapid temperature change. If I leave a flameless heater that was cold at room temperature, it will eventually get to room temperature. If it gets way above room temperature, that's odd. Something weird's probably happened. But if I lay it, if it's 30 degrees and I lay it out here, and in 3 seconds it's room temperature, that's weird. Something else is most likely, I'm not making a definitive statement, something else most likely is going on, and that's what we want to investigate, right? So, if you open your packet up like this, staples over here, you will see two things. You will see MRE, and you will see hot hands. There's graphs. We're going to take temperatures every 3 minutes. The temperature goes under, to start with, minute 0. That's your initial reading. So our first temperature is going to go under 0. That's our initial reading. Also, we want to get the initial mass, the starting mass, and the starting mass, and any initial observations we can make. Okay? So we're going to look at the flameless heater and the hot hands and make any initial observations. And then I am going to put them in these cups. I'm going to add water, obviously, to the flameless heater. I'm going to put the lids on the cups. What does that do? It's not going to make it a closed system. Okay, the system's still open. These lids are not perfect. And even further, I'm going to shove a thermometer into it to measure the change in temperature. This right here is my other camera. I will switch to it, and you'll be able to see the hot hands and flameless heaters, and you can watch the temperature change. You know what? I was going to just record. I think I will pause and unpause the video every 3 minutes, the recording, so that you don't have a huge video, and it'll shorten my file upload, so that'll be nice. But you will be able to get that data, and the data for your chart is important. And at the very end, what we need, if you're looking at your paper, your final mass in any final observation, and your final mass in any final observation. Once you have all the data, and this goes back to, I can use data, I can chart data and use that to explain a phenomenon. We'll turn to the back. There are 2 charts, one for hot hands and one for the flameless heater. You will chart your data. It's very simply, every 3 minutes, put a dot wherever it is and then connect the dots. Or you can shade the boxes if you want. It doesn't have to be perfect. But we want to see how fast they rise and fall, especially compared to each other. And then down at the bottom, list and describe any and all similarities and differences you notice and observe between the 2 systems. So anything you see that's different, between their temperature, between the speed of change, between mass, between whatever, write that down. I expect you to do at least 2. You know, I like to do things in 5s. If you can come up with 5, that's awesome. But you should get 2 very, very simply and quickly. Let me go ahead. I'm going to pause this for a second and start getting the materials over here ready, and then I'll bring you right back. Okay, so I went ahead. I got the flameless heater. These are a little bit different. These are made for food, like commercial food, so they go under trays to keep the food hot. Like if you've ever been to a buffet that had like the metal trays. Same ingredients, so nothing to worry about there. I got the hot hands here. Got my 2 cups. Let me make sure my thermometers are on. They're both reading about the same temperature, so that's good. We don't want any observation bias there. One thing to note, as soon as I open the hot hands are air activated. So as soon as I open them, they're going to start reacting. So I'm going to put the hot hands on as quick as I can. Let me get the scales turned on. And again, I'm going to tell you this, then we're going to switch to this camera so you can look down and see what's going on. I'm going to put the lid on, put this in, it will be about here. So it won't be touching the hot hands or the flameless heater. That's hard to see. It's going to be about here. So it won't be touching the hot hands or the flameless heater. We're measuring air temperature. So I'm going to go ahead and switch cameras real quick. Let me click the button. That button. That was silly. That was not what I needed. That button. Optics to this. Perfect. Okay. So this one is hot hands. This one is flameless heater. Let me do this as quick as I can. Start getting the hot hands out. Hot hands go in. Well, that's great. It took me a minute to put that open. Let's get the hot hands in there. Get the lid on the hot hands. There you go. Get the lid on. We're going to add the water to the flameless heater because, you know, that's important. We're going to get the lid on the flameless heater. Don't worry about the initial mass yet. I'm going to do it with the thermometers in it. That way we kind of have the same thing going on all day. This is how I did it in class for everybody. Make sure you can read these thermometers. Okay, so the thermometer started almost exactly at 23 piece. The initial flameless heater mass. Initial flameless heater, I got to keep it on the scale or it's not going to read right. The initial flameless heater mass is 61.9 is what it said. Sorry, flameless heater mass is currently at 62.1. 62.2 for the hot hands. That's a coincidence. Okay, so we're going to get our initial temperatures. We were right at 23 for both. Hot hands is currently, make sure these are in the right place in the cup. Hot hands is currently at 23.8. Can you read that? And flameless heater is at 23.9. So good. They're both right at 23.9, 23.8. Now we just clicked to 24. So right now they're about exactly the same. We have our masses. Let's go ahead and I'll pause this. Let me get the time. We're at 2, so I put these in at 2. Okay, we are back. I made a note here to myself, it's right at 3:05. We've been 3 minutes. Air temperatures right now, hot hands 26 degrees, flameless heater 27 degrees. This flameless heater is getting a little warmer. You can go ahead and pause it right here if you want to leave that on the screen. I'm going to pause the recording and come back in a couple of minutes. Okay, we are right at 3:08, so this is your 6-minute temperature observation. Your 6-minute temperature observation. 27 degrees for hot hands, 59, and now rapidly rising for the flameless heater. So 27.1 for hot hands if you want, and 60 for the flameless heater. So if you want to pause it right here to get those written down, you can. And I, again, am going to pause the recording. So you can pause it, and I'm pausing. Okay, it is about 3:11. Whew. You can't smell the flameless heater, but I can. The hot hands still increasing, I believe, slowly, 27.8. I'd really like it if it clicked up to 27.9, just so I can make sure it's still increasing. And flameless heater right now is at 75. So your observation for 9 minutes, 27.8, it went to 9, and 75, and it's still rising, but it looks like flameless is slowing down a little bit. But they're both still going 9 minutes in. So one of the questions that you all had for your driving question, how long do these work? How long do they go for? How many times can I reuse it? So reusability is, I mean, I know with hot hands, reusability is pretty low. Flameless heater, I'm not sure. But right now we know the reaction's still going at 9 minutes. So you can pause it here if you want to get that data frozen on your screen. I'm going to go ahead and pause it myself in 3, 2, 1. Okay, we are right at now 3:14. This is your observation. Well, we fell over. because the lid is getting, oh, did you see the steam or the hydrogen, I guess? Yeah, we're getting warm, so that lid's even getting soft. It's hard to hold it up. So I'll hold it up for you. I'll try. So we're at about, it was at 75. 76.8 for the flameless heater. Hot hands still holding strong at 28.4. So this is observation for 12. I'm going to pause in 3, 2, 1. Okay, we are back. This is the hottest flameless heater we have seen all day, and it is nearly to boiling point. So yeah, boiling point Celsius is 100. I'm really curious if it's going to get there. It's probably not good for the cup if it does, but it explains why the thing fell over. Hot hands currently sitting at 33.3 degrees. Come on, flameless heater, you can do this. And its final reading for the hot hands in your minute 15, for the flameless heater appears to be 94.4 and holding strong. Wow, okay. The other highest temperature today was like 70 something. So this one, I must have got it good and saturated. It's going pretty good. Oh, hot hands just clipped up. So let's go ahead and get our final masses. So we started with these masses, right? These were initial masses, almost the same, which is awesome. It hadn't been that good all day. So I'm going to take these off. We're going to zero the scales. Remember, we always zero our scales. Why do we zero our scales? To make sure we didn't mess it up. Let's get the flameless heater first. Wow, okay. So its initial mass was 62.1, and now it is 60.8. Wow, that dropped quite a bit. Our hot hands, its initial mass 62.2. Okay, I don't know if you can see that. Well, hang on. Its mass 62.5. It went up. Let me take this off and zero, because if we see something we don't really expect, we verify. I zeroed. $62.6 again. 62.5. So it went up 62.5. So hot hands went up by 0.3, 0.5%. This dropped 1.9, hang on, no, that's wrong, 1.3 degrees. And it's starting to cool down a little bit. So may have been where I moved it around. Excuse me. So that is your temperature, your beginning, your initial and your ending masses. You should be able to chart that on the paper. Let me move these off. I'm trying to set this over here with a test tube in it. If you notice, I really like hydrogen, and I like blowing things up. So let's just move these for a second. So you should have this data, your starting mass. Come down here. Camera, focus. Yes. Your starting mass, any initial observations, and your temperature. You didn't really see any appearances. I smelled some. I'm not sure where it was, but I told you when I started smelling it around here. Appearance, the cup right here started to fall over. Right here, the plastic got so soft it fell over. We started seeing steam come out. That steam we were getting close to boiling point, so it might have been a little bit of actual steam, but it's probably mostly hydrogen. Other observations, yeah, the appearance steam fell over. Other observations, steam. Final mass, again, flameless starting mass 62.1, ending mass So that's where those go, starting, ending. Let me write the same here to make sure you know which one goes where. So now we're on the hand warmer side. So hand warmer side, I didn't really smell anything from the hand warmers, but I think that's by design. If they smelled bad, people probably wouldn't buy them. And we gained a little bit of mass here, right? So that's something you might want to put in your final observation. You've got the temperatures. You can pause the video or go back. Appearance, I didn't see anything change. Also, it's in a styrofoam cup, so it's hard to see something change. Other observations, I don't really have any for this one. Comparing the temperatures, after about 3 minutes, did it rise anymore? I don't remember, but you have them all charted, or you have them all recorded, so get over here and chart them in. Flameless heater, your initial temperature, and then we ended way up here. I don't remember the initial, but we ended way up here. So where is it in between? Chart this, and I don't remember these either, but you have them, but I think it probably looks something like this. I don't know. This is not good enough. You need the real actual points. And then down here, describe anything you notice that's different. Well, I can tell you, I noticed that immediately. I can tell you if these trend lines are what I think they are, that's a difference. What other things did you notice? I told you I had a smell, I saw steam, all of that stuff. So those are things you can notice that would make sense. And other than that, that's pretty much what we did in class today, is that investigation. So give me a minute and I will pause and come right back on the other camera. Okay, so I'm back on the big camera. Yeah, so we saw something, right? We saw two systems, both increase in heat. I'm not gonna sit here and mess with you, but we were sure at this point they're both chemical reactions. We saw temperature change with no other way to explain it. We saw gas coming off of the flameless heater. Yeah, so we have two chemical reactions, but they did something different. And that's kind of the weird part. One gained mass, one lost mass. That's weird to me. Like, I would have expected the same thing. I have the same outcome. Why didn't I have the same, does that make sense? Like, I have the same outcome, but I have two different paths to get there. So that's kind of odd to me. With the hand warmer, we didn't see or hear any gas. There didn't appear to be any. Yeah, the easiest evidence that I can tell you that I think it's undergoing a chemical change is the rapid heat transfer, or sorry, the rapid heat increase. So let's think about the energy transfer for a minute. And I said energy transfer, this is where my mind is going. For energy to transfer from one thing to another thing, we talked about this in my class. Temperature, average kinetic energy of the particles. Temperature always transfers high to low. If I have a hot drink and I put ice cubes in it, you'll probably say, oh, the ice will cool it off. What's actually happening, high to low, the hot drink is heating up the ice, okay? The energy is going in, heating up the ice is melting, and the average temperature between your volumes and your temperatures, you'll eventually reach an average. But the ice doesn't, while it does cool the drink off, scientifically we want to say the energy transfers from the hot thing to the cold thing. So when we talk about energy transfer, it's always hot to cold. So think back to the model, or initial model. We started moving the particles. How do we follow that energy transfer now? So you had, let me grab it. Oh, it's over here. You have on their consensus model the food with the heater behind it. How does that energy transfer? Obviously, we're not saying the food is trying to cool down the heater. That doesn't make sense. The heater is, bell, give me a second. Okay, so an interesting question. I'm sure the bell's gonna ring again. An interesting question. I know how much I heated up the air, right? And if I put it in contact with the food, like I did in the other video from lesson 1, I measured the temperature of the food. The neat thing is the food was hotter than. No, because I did that in Fahrenheit. So 132 divided by, so that's 100 divided by 9. Let's call that 11 times 5, 55. So I got it to about 55 degrees C. So even though the air was hotter than, I only got it to about 55 degrees. Why is that? How does temperature or how does energy transfer? And we measure that in temperature. I'm going to try something just for fun. I'm not sure this is going to work. Yeah. I have this other test tube over here collecting. Okay, they announced the first load of buses. So, I don't know if this is going to work, but I like trying to light things on fire. Hopefully this is hydrogen gas. If so, oh, I didn't get enough. Sad joke. I was just trying to, be interesting. So let's talk about some other questions. Things that this leaves me wondering. Other chemical reactions, things that you might do at home, like when you clean or something. Do those reactions heat things up? Right? Like when we take bleach and clean the top of the stove. I have a bleach cleaner, I have a glass top. So does that heat something up? Is bleach doing something? Does hydrogen peroxide, it bubbles. Does that heat something up? If I put bleach and hydrogen peroxide together, which I'm not going to do because I don't know what it does, would that do something? Like the bath bomb, we're releasing energy. Is that right? Like, did the bath bomb release energy? Is this releasing energy? If we found a different set of chemicals that released energy, could we heat food up with that? So if you're like stranded in zombie apocalypse land, could you find something to heat food up with? Does energy always flow out of chemical reactions? These both did. So does it always come out of chemical reactions? Could you ever have too much energy coming out of a chemical reaction? We almost melted the lid of this thing. Like that's, yeah, that's soft. So maybe, it depends on what you're doing with it. This got close. There's a lot of questions this kind of leaves us with. But I like the zombie apocalypse one. If we were in zombie apocalypse land, could we find some other chemicals or other things to heat food up with? We don't have matches or lighter that we tried to light the hydrogen on fire with, quit working. What do we do? What do we do? Can we do something? And that's pretty much all I have for you. And I hope you enjoyed it and got through it. Bye.